Hey, Matt.
Hey, Mike.
Want to do some more Advent of coding?
Advent loosely. Nope, that didn't work. Yes.
I don't. Just a simple yes would have been fine. All right. Welcome to Hacking the Grepson. We are covering week 2, at least according to us, how we arbitrarily decided to split it up this year. Of
Day 1 through 7 is week 1.
Yeah,
arbitrary.
Well, but I mean, we could cut it up into any number of days. I don't know.
Perhaps we will next year.
Oh. So yeah, we're doing week 2 of Advent of Code, which is day 8 through 14. Advent of Code, once again, is that annual Advent calendar of programming puzzles put out by Mr. Eric Wastel, who's been doing it for, I guess, 10 years. Way to go, Eric. Thank you for this wonderful puzzle challenge. If nothing else, it gets me to think about algorithms and graphs when I don't think about them all year, generally, as a web dev. But so speaking of not thinking about the things that the Advent of Code is asking me to do, definitely with part day 8 and on, give or take days here and there, I definitely struggled and didn't solve a lot of these. I tried some of them. I think day 11 I actually got, but all the other days I tried and failed or didn't even get to. Because, the only problem with Advent of Code being around December is that, there's Christmas and there's still work and other things. And I want to give all my time to this because it's such a fun endeavor, but I never have as much time to work on these puzzles. And as they get harder, I just kind of lose momentum at some point. And my momentum was about now. I think yours was later. But
mine was 1 week later.
1 week later. Yeah, there you go. And then we have other friends who are just like somehow barreling through the whole thing no matter what. I don't know how they do it, but props to them. So anyway, let's just jump right in to day 8, which is called resonant collinearity, which is a very fancy set of words. And what we're doing right now is the first sentence of the day sums it up. You find yourselves on the roof of a top secret Easter Bunny installation. And on the top of, on this roof is a bunch of antennae, or antenna? I don't know.
Antennae, I think.
Yeah, I thought it was in like AE at the end, but they use antennas for plural. Anyway, it doesn't matter. So you get a puzzle input, which is another 2D grid of cells. Once again, the dot or the period meaning nothing there or blank or empty, and then you have other characters, and in their example, they have the number 0 and the letter A. Mm-hmm. And these represent different frequencies, different antennas on different frequencies. So the zeros are all the same frequency and the A's are all the same frequency.
And those are capital A's because case matters in this one.
It does. These very specific ASCII code for the character matters. And what you're trying to do in part 1 is, and I must say, this was yet another one that, like, the first few times I read it, I was just like having a really, really hard time struggling, just figuring out what they wanted and what I was supposed to get out of it.
I wrote in my notes that the description of this problem was the most confusing one of the year so far. It was not clear to me what we were trying to do. It took several iterations of reading through this before I figured it out.
Okay, well, that makes me feel a little
bit better. You're not alone.
All right. So, but in the end, what I grokked from this is that in this grid of these antennas that have different frequencies, what you're trying to find out is the antinodes that these antennas create. And the antennas create antinodes when two antennas of the same frequency, for example, the capital A frequencies, are at least how do I even say this?
One is two times as far away as the other.
2 times as far away as the other one, right? And so if you were just looking at a 1D grid, so just the X and no Y, let's just say you had an A at like the second position, and you had another A at the fourth position. Those two antennas are twice as far away from each other. Yes?
So you have to
From
have
each other.
There's a third point involved. The antinode is the thing. So the antinode is 2. If you put the antinode at 0, right, then you've got 0 to 2, that's 2, and then you've got 0 to 4, and that's 4, or 5, however the hell you're going to count it. And then there's one on the other side of that, which is 2 away from 4 and 4 away from 2. It was a very confusing one.
Right. I mean, in a 1D chart, it's somewhat grokkable, but when you add a second dimension, it gets a little wonkier. But to cut to the chase, you have these two frequencies. They're creating antinodes that are like in line with them, but in a 2D grid. Like if you were to draw a vector between them, beyond the first one and beyond the second one in the opposite direction, they create these antinodes, and you need to count up the total unique locations that contain an antinode. That was something I'm just now noticing that says unique locations. I don't know if that actually comes into play because, once again, I didn't actually finish this one. But Matt, enlighten me, please.
Okay, so let's see. So to deal with the duplicate thing, I used a set.
Okay.
So I didn't have to think about it. I just dumped positions in that were antinodes. So I was like, great, I don't have to think about it. The description was by far and away the hardest part of it. Like, understanding what you were supposed to do was harder than the actual algorithm. I sketched out a rough algorithm on my whiteboard for this one. I looped through all pairs of nodes, removed non-matching pairs, then removed pairs that are not in a line, which incidentally was really stupid because as I thought about it later, any 2 points are a line.
Yeah,
So
you can
just
draw a
all
line
matching
between 2
pairs.
points.
I was trying to figure out, like, I was trying to make them on like perfect diagonals, like 45 degrees, and I was like, oh no, some of their examples are like, this one's at 1, 2, and this one's at 3, 7, and so there's not, but they're in a straight line.
Yeah.
So that screwed me up for a while, but once I figured that out, I calculated the distance between nodes of the pairs. And then
that uses the Manhattan distance, right? Because I'm not sure if we
I
brought
don't
up
think
that.
it mattered here. But
Well, so then how did you find the distance, if not
I think
through
I
that?
did use that. Let me see. What
Okay.
did I use to find distance? Hang on. So yeah, I'm doing the Manhattan method. So how many X over, how many Y over, basically.
Okay.
For doing that, I did not make a new class for this. I just used my grid and position classes and a lot of stuff. But basically, I have a triple for loop.
Oh, Lord.
Where I go through all the frequencies, so I added a new function to my grid, which basically let me look up all of the frequencies or all of the values in my grid, all the positions in my grid that had a certain value. There we go. So I used that plus what the values were. Basically, I rearranged how I was storing them in my grid to make it more useful that way. I have now 2 things. I have position to character and character to positions, which makes a lot of the stuff I had to do a lot easier. So I loop through the frequencies that are available. I loop through all of the antennas in that frequency -1, and then all of the ones from that point on. So I'm getting all the pairs. So that's my 3 loops right there. And then I just did 2 times the first minus the second one, and 2 times the second one minus the first. And if that was in bounds, then I added the tuple to my set, and then I just returned the length at the end. It turned out to be really straightforward to do once I understood what the problem was. And that it really did boil down to, okay, I know the distance between these two, and then on either side of them, half that distance away, is there a point? Like, is that point in bounds? Great. There's an antinode. That is literally all it was. It was such a confusing description.
Yeah, I tagged this one with a word problem because it definitely a huge obstacle was just kind of grokking what they were asking. And even though I didn't get it, when it came out, and at this point I was not necessarily doing them as they came out, I did work on this one a little today, and I was starting to augment my grid class to do a lot of the things that you were talking about, is like, finding all of the positions of a specific character, and then finding pairs of those, and then finding distances, and then I was going to get to actually finding the antinodes. So I think it is possible that if I kept going with this one, I would get through part 1 at least.
Oh, for sure.
But now I'm curious what part 2 has to throw at me.
So part 2 had another really confusing description in it, but it boiled down to, I'll read the opening sentence because it tells you what you need to know. Watching over your shoulder as you work, one of the historians asks if you took the effects of resonant harmonics into your calculations. What that boils down to is take any pair of notes, doesn't matter, any pair of antennas, doesn't matter the frequency. So then you take that line, and the distance between those nodes, you'll have antinodes. I think they still called them antinodes for the resonant harmonics, that are that distance away from on either side, right? So if you have 1 and 3, which are 1 away on your straight line, you'd have one at 0 and 4 and 6. Or sorry, 0. So you have 0 would take you to 1, and then that has you'd have to be 2 and 4 for that to work. So you have 0 to 2 is 2 away. Then 2 to 4, that's where the frequencies are. That's where the antennas are. Those are 2 away. And then every 2 spots after that, right, it's a line. You're basically doing the line separated between every 2 antennas, separated by the amount between those 2 antennas. So if they're 1 away, every position on that line.
Okay.
I think it involved the distance between them, but it might have actually just been the line, and it's the way the grid works that they ended up spaced apart. I might be getting some parts of that wrong. This actually was easier to calculate than the first part. I was about to say,
it doesn't sound too terrible.
But you had to find all of the antinodes for every pair of antennas, which was
not
more,
just matching
obviously.
Antennas, right?
Right. So it's more, but you don't have to worry about the twice the distance stuff, and you just have to find all the inbound positions on the line, and you're more likely to have ones that overlap here. So if you didn't solve the overlap problem, so you're not double counting in the first problem, you're going to have it here. I, again, just used a set. So this is actually also a triple loop, but a different kind. Oh, I kept the same loop structure just to make my life easier. I just started from this frequency, find all antennas. Oh, it is of the same frequency. Okay, sorry.
Oh, so they didn't get rid of that.
Okay, they didn't get rid of that part. They kept the frequency part. They just got rid of the distance. So scrap half of what I said.
The whole double distance thing, I wasn't sure because I was actually looking through my input and I didn't really notice that any like of the same like characters were right next to each other. So it almost seemed like a red herring that mattered. Maybe it doesn't matter. It just, I don't know.
No, it does, because it's the antinode's distance from one and the antinode's distance to the other. That is what you're calculating. It's not the distance between each other that matters. You use that to figure out where the antinodes are. But in this one, it's just all of them in a line. Every point on that line added in. So I got rid of the 2x logic. Otherwise, so I actually have a fourth loop inside of this one. So I've got my frequency loop, my I loop, my J loop, and then I have inside of that 2 different while loops that are not nested within each other. One checks the antinodes on one direction, and the other checks the antinodes in the other direction until I hit the out of bounds, just to make life easier. I just calculated where they all would be until I hit out of bounds. This one, I'm very curious how long this took. This one took, oh, I'm in the wrong directory. I'm like, this also took 18 seconds. Amazing. No. That was from last time. This is problem. So this one was super fast, actually. Even with my quadruple loop, it was 0.009 seconds.
Nice.
And part
like
one...
9 milliseconds.
Yeah. Part one... So part one actually took longer. It took 0.01 seconds. I know, right? That's so that the calculation bit of it took some time, I guess. But otherwise, this one wasn't too bad. Find all the inbound positions on the line between each 2 nodes of the same frequency.
Well, thank you. That was day 8. Let's move on to day 9. Okay, day 9. Disk defragmenter. Okay. Yeah, so this one was interesting to me mainly because it actually felt like a very computer sciencey question or puzzle. Like essentially, like how do you pack in as much data into as little data as possible? Compressing the information about something into what they call your puzzle input a disk map. So my main issue with this one is that I never quite got around to the proper data structure. And so all my time spent on this just ended up being for naught. Because I did actually like get a solution, but it was too low, and that's probably because the data structure was wrong. But so on this one, disk defragmenter, another what they're trying to get
fragmenter.
What did I say the wrong thing?
Yeah, it's not a defragmenter; it's a fragmenter.
Right, but the
That
puzzle
also threw me off.
Wait, is the puzzle not actually called defragmenter? Did I write that down wrong? Oh my god, I totally
I
wrote
also
it.
called it defragment, like when I was solving it, and that's not what we're doing here.
Oh my god, you're right.
And that
We are
comes into play in
fragmenting.
part 2. It's the only reason I noticed that.
Okay, you're right. It is actually called disk fragmenter. I completely assumed that it said defragmenter. It was that double D thing that just got stuck in my head. So your disk map is this line of numbers. And the actual input, like the sample they give you is like, I don't know, maybe 15 numbers long, but the actual input is, I don't know, hundreds and hundreds of numbers all in one line.
And those numbers expand into your actual data that you're operating on.
Right. This is the map. This is the compressed version of your disk and the data that is on it that you then need to process into what, I need to eventually do. I created a class called disk, and I was reading in the input and trying to build the data structure of your disk using this map. And I don't really remember where I ended up, but I think I was not actually creating the correct data structure. So when I actually went into fragment it, which is like you take the map in, and it says that using a dense format to represent the layout of files and free space on the disk. And so a very simple disk map would be something like 1, 2, 3, 4, 5. But what that's really saying is that the first number is what the
number is. So it's the size of the file, and then the next number is the amount of free space after
Free
it.
space,
And then
right.
the next number is the size of that file, how many blocks it takes up. And then, so it alternates between size of file and
Right.
size of free space after file.
right. So 1, 2, 3, 4 is like a 1 block file, 2 blocks of free space, 3 block file, et cetera, et cetera. And then they show it in a different way where they show like a
0.11
right because each time you move from one block file to another block file, the ID of that block changes and they start with 0. So you have a 0, which represents that you have a 1 block file with ID 0, and then you have 2 dots because you have 2 blocks of free space, and then you have 3 ones in a row because that's the next ID of the block, and you have 3 files in that, and then 4 dots, and then 5 twos. So, I mean, already, this is dicey.
Yep.
And so once you realize, and that's the thing is, I think I was trying to make my data structure based on that second part, when I should have been. I just wasn't thinking about it correctly. But in the end,
I did the same thing.
Okay. All right. But if you have the right data structure, regardless of how you end up getting there, what the puzzle is actually to solve is moving all of the files, all the file blocks next to each other. Like essentially like take the stuff from the end and move it towards the front, filling up the free space that's in between the blocks. So all the dots are now going to get block file IDs from the end of the disk, and you just keep pushing them towards the front of the disk until essentially you've used up all the free space, and all you have is a bunch of block files and then a bunch of free space at the end. At least that's how they show it in the text. And then
So basically you're breaking up the files, but condensing the amount of used space. So you're like splitting up file 2 and putting part of it in between 0 and 1, and then putting the
Right.
rest of it afterwards or whatever.
I mean, was this hard for you, Matt? Because it definitely was hard to even get as far as I got.
Yes.
Okay. All right. But you did figure out both parts. I did. So I feel like the only part where I really failed on not even getting part one is just misinterpreting the data structure that I was trying to create, so that when I went to do the fragmenting, I was fragmenting the correct data structure. I think I had the wrong data structure. I figured out a way to fragment it, even though my method is called defrag because I read the title incorrectly.
Mine was also called that. I'll explain why it's not called that in a second.
But then in the end, once, I was able to get a display of the files moving to the left, like in the example that they show. But obviously, that's not the actual data structure of this disk. That's just how it's viewed when interpreted, at least. That's how I feel like why I didn't get it right, because I was
and that screwed me up big time.
Okay. But you figured it out in the end.
I did. So I'll go through my notes here. I thought this was going to be pretty straightforward right from the beginning, but also I noted that it's a really inefficient way of defragmenting a disk, because
You're not defragmenting, you're fragmenting.
Yes, I didn't realize that, because it splits up the files. That's the opposite of what you want to do in a disk defragmenter. I remember running defrag on my computer constantly. I was always trying to keep that up because my computers always sucked. And my gut feeling was part 2 is going to ask us to defragment differently. And I was right. So they basically give you the algorithm for what to do here.
Yeah.
You just have to do it, but it's more complicated than that, of course. This was the first problem of the year where I submitted an answer that was wrong. In part 1, no less, which is particularly rare. Usually, you run it for the sample works, you run it on the input, turn that in, good. Not the case for this one. And the big reason is if the file ID is greater than 9, which it is never in the sample, but it is here, then when I store that number, I can't store the number 10 in one spot. I mean, I could have put A or something, right? But that's going to only give me up to 15, depending on how I do it. And that screwed me up, because then I was putting a 1 somewhere and a 0 somewhere when I should have been putting a 10 somewhere. So the fix to that was I kept the same data structures, and I'll describe those in a moment. But the fix for that, I ended up printing out lists, or like I put brackets or quotes or something around it when I printed it out, and then I was moving that entire block instead of things. So I created 4 classes for this one, specific to this problem, which is very unusual for me for this problem. I had a disk map, which was the thing that took in the original input and then built everything else from there. It has the bulk of the logic behind it. The other ones almost entirely exist for me to be able to print this thing out and think about it. They don't have anything beyond like a string and a representation function. So I have a disk sector, a disk file, which is a disk sector is anything that shows up in the disk. Like it's a spot in the disk where you can put things. I probably should have called them disk blocks or something, but they had file blocks, so I called them sectors. Then I had disk file, which is a subclass of disk sector, and is always a file, and it has a file ID associated with it. And then I had a disk blank, which is just the blank spaces. That also goes from disk sector. And then the checksum was easy, and so my defrag function, as I called it, later called reorder, what I ended up doing was it iterates over from the beginning to the end, and then if it's already a thing, then I keep the block there. Like if it's already a file, if it's not, then I go to the end where I'm also keeping an index, and I grab the last block from that, and I don't store it as 10 in a printed out thing anymore. I was using my string representation to do all this. Instead, I had to actually keep a string of these disk files or whatever I called them. So I just did the algorithm, but I had to do that specifically to make it work. Ultimately, not terrible to do, but just a pain. That 10 thing really screwed me up. I ended up making a sample file that had more than 9 file IDs in it so that I could, or more than 10, so that I could have this problem and make sure it worked. Part 2, he's like, hey, this is a really inefficient way of organizing my disk. I should defragment instead. And I was like, what? And then I went back and I reordered. Yeah, so I called the defrag. In retrospect, I should have called my defrag fragment, but I called it reorder because that made more sense to me. And then I made a new defrag method. So this one, what they want us to do is rather than moving individual blocks, you're moving entire files. So you're still going basically from the end, and you're putting it into the first, from the beginning, spot that entire file will fit into. So if it's 4 blocks long, you have to have at least 4 blocks to put it in there, and you put it at the left end of that. And then if later you have a 1 block size one, it can go in after that if there's still room, right?
Oh, so wait. So if you're pulling like a 4 block thing from the end and you're moving it towards the front, but the first available one only has 3, it skips and goes to the next one that's big enough to hold it?
Yes.
Oh, okay.
Yeah. So you end up with things in a different order. Much better defragmentation. This was relatively straightforward to understand, but a pain to implement. Let's see. I ended up splitting blocks. Oh, so I originally just had disk block or something like that. I ended up making blanks and files. That's where those extra subclasses came out. I didn't need them for the first part. I needed them for the second part. And then I used the zip function in Python to zip them back together, which basically takes one element of one list and one element of another list and puts them together in a tuple. So I made a list out of that. Found out a really obnoxious thing, which is in Python at least, zip does not pad if the lists aren't as long as each other. So if you have one list that's 5 and one list that's 6, you lose that last one, which is really important for this problem.
That seems like a bug.
Yeah. Well, so they have a built-in version in their iter tools thing called zip longest, and then it does pad. So I ended up using that. So I learned a new thing. Great. Basic algorithm for this one was start at the end of files and then iterate through blanks until I found a blank size that was bigger or equal to my file size, and then had to change things at both ends of the list to make it work. The original blank section is replaced with 0 blanks because, again, you have to go with – because you have to do the checksum, and the checksum operates on the disk map, if I remember correctly, or something like that. So, I had to add 0 blanks when I would move things from one to the other. I couldn't just go file. I had to put a 0 blank and then put that in there. And then on the other side, I had to replace it with 0 file and then file size blanks. So that I was basically I was swapping them. But I had to add that 0 length thing so that they were still actually kept correctly. I got derailed for a while worrying about situations where how I would represent the files using the original disk map. So if I had 0, 0, and then 3 blank, and then a 1 blank, and then 2, I was worried that how I would represent that would be wrong, but it ended up being fine. So I spent a lot of time going down this red herring route that was not relevant at all. If I'd bothered to clean up my class, I think it might have mattered, but I didn't care at this point. Instead, I just shoehorned in the checksum and left the class in a messy state. Oh, right. I did not clean up my class, so I'm copying my class every single time for this one, and then running the defrag to do it, and then returning that instead of and so then my map is all screwed up, but I don't care. I submitted this in a way that I would never do in real life, basically, where my data structure ends up in complete disarray. But I did not do that. So I even have a to-do in my class. I'm should rebuild everything instead of leaving the map broken and making a new checksum here. But I didn't care. This was the start of the derailment for me for this year, where I went okay, I'm starting to get it's starting to get too hard, kind of thing.
Was it too hard, or was it just too much to do? I don't know.
It started to take a really long time. Debugging it turned out to be was really hard. It was complicated to understand. Yeah, not this one. The previous day was complicated to understand. It was a lot to do, and I've been very busy at work, so it became difficult to pull off.
Yeah. I sometimes wish that it didn't happen this soon, but it seems to happen about this time. Like, once again, if you look at the stats of like how many people are actually submitting things, this is easily probably just after where people start to like the number really starts to drop because
I would love it if he pushed out the hard ones a little bit later because I want to do more problems. They're fun.
Yeah.
But it gets to the point where I'm like, I just am not going to spend my time on this.
Yeah.
I will spend, however, hours talking to you about it.
And that's all I care about. So let's move on to day 10. It's called Hoof It. We're now in a lava production facility on a floating island in the sky because, of course, we are. And one of the reindeer is holding a book titled Lava Island Hiking Guide. And when you open the book, you discover that most of it seems to have been scorched by lava. Oh, no. And you're going to ask for help. And he gives you a blank topographic map of the surrounding area, which is your puzzle input, which actually looks like another 2D grid of numbers. And each of the numbers indicates the height at each position using a scale from 0 as the lowest and 9 to the highest.
We had a problem that was shaped this way, I want to say last year or 2 years ago.
Yeah.
And I hated it. So I was really worried when we walked into this problem.
Yeah, well, what it made me think of is actually one from the first year that we started doing this, 2021, day 15, called Chiton or Chiton, Chiton, and it was all about. It was a similar kind of grid where you were trying to essentially like find the best path through a grid based on the numbers, and it was talking about a risk level instead of a height level. But yeah, very very similar, and I never even attempted that one because I looked at it. I'm like, this seems like a graph search kind of problem, which normally involves like either a breadth first search or a depth first search or I don't know, A star, Dijkstra's formula, some kind of way of like going through a grid, moving from node to node, using some kind of a heuristic, like it's okay to move here, it's not okay to move here, and then finding out like the best path through that grid. Like that, I mean, even though I didn't work on it, I mean, I can still look at these puzzles and sort of get like the gist of what I'm going to need to know to work on them and know that I'm weak in that. I'm going to have to research this and I'm going to have to think about it and it's going to take a lot of time and I don't know how to do it. And so that's why this one went undone. But what was your experience with it?
So I generally don't like route finding problems. I don't mind doing a recursive depth first search. That's easy for me. I can just do that off the top of my head. Okay. Anything else I have to think a little bit more about. I'll do a breadth first. I hate doing Dijkstra's algorithm. It's not hard. I just don't like doing it. I don't find it fun. I just don't enjoy doing route finding problems. They're not interesting to me. It's a solved problem. People have already done this.
Is this why Mazadol is still not done?
That's one of many reasons. It just wasn't interesting to me anymore.
Yeah. Okay.
I do have a new idea that I'm going to try to make myself do next year. It probably won't happen.
So how did you approach this one then?
So I had some time before I took my daughter to school to work on this one that day. So I ended up sketching out a quick algorithm on my whiteboard in pseudocode, which I actually wrote down, which was parse into a grid, set n to 0, and then find all the trailheads, which was find zeros, right? So I got a list of all the zeros in my grid, and then I got all my neighbors for that position that were one more.
Right.
And of course I needed to have an end condition, which was if my number was 9, then I returned success, otherwise I returned fail. Rereading the problem statement, I had missed the fact that I couldn't just stop at the first 9 I found. I had to count how many I found, because that was how you scored it. Was like, how many ways are there to get to a 9 from this 0?
Right.
Basically, that was pretty easy to do. I just I had to do a little bit more than I planned since I couldn't just stop at the first 9 I tried, but I needed to keep track of how many I found. It was an easy modification. Pretty straightforward. I don't even think I didn't even make a class. I do have a depth first search, which is recursive, because that's the one I like to write. That's how I think about it. I'm like, okay, go as far down as you can. Okay, that didn't work. Go back until you have another path. Take that route. Go as far as you can. Okay, that didn't work. Like, It's easy to recurse that way. You can do a recursive breadth first, but then you have to start keeping okay, here's all the next level. Keep track of those, and you have like stacks of I like the code to write the stack for me, basically.
Okay.
So it wasn't too bad. Part 2 actually wasn't that bad. It changed how you... So the reindeer found another slightly charred piece of paper that had different way of rating the number of distinct hiking trails, which begin at the trailhead. This one was... Oh, this one was the one that was... Okay, so the previous one counted how many 9s you could get to from the zeros. This one counted how many different ways are there to get to 9s from zeros.
To all the 9s.
All of the 9s that you can get to from each 0, how many distinct ways are there to do it? So each trail isn't how many 9s can it get to, it's how many ways can you get to 9. So it's like all the different paths you could take to get there.
Okay.
Which is generally a big, like kind of a pain of a problem, but it wasn't too big of a shift for the way I wrote my code.
Okay.
I almost did it as part of part 1 anyway, when I was doing it. And then I realized about halfway through this was really ideal for like a dynamic programming type, DP type problem. But I don't enjoy doing those. So I didn't do it that way. And it turned out actually to be easier than the depth first search that I originally wrote. I just returned a 1 every time I hit a 9 and summed them instead of like keeping track of where the 9s were. I just said, oh, I reached a 9. Great. And then I went back up to another path. And if I found a 9, great. Depth first search worked perfect for this one. Didn't require DP at all. It was very fast as it was. I liked part 2 of this problem better than part 1. I like when the part 2 works with my original solution.
Right.
It doesn't require complete rewrite.
Yeah. Okay. Excellent. Day 11. Okay. Yay. I got this one, at least part 1. And my first thought was, this one's called Plutonium Pebbles. And my first thought was, OMG, lanternfish again.
Yeah.
And the part of it, and I think it was just like that one. So the lanternfish was a previous puzzle in our first year that we covered, 2021. And the first part of it can be done with brute force, which is how I did it. But what they're asking for you is you basically have a line of stones, and they each, basically every cycle, they use the idea of you're blinking. Every time you blink, the stone's status changes. And so if it has a 0 on it, it changes to a 1. If it has an even number of digits, it gets replaced by 2 stones. So the left half of the digits go on the new left stone, and the right half go on the new right stone. And then if none of the other rules apply, the number on it gets replaced by 20 or multiplied by 2024, because that's the year that Advent of Code is right now.
It's like a one-dimensional game of life.
Yes.
Not the board game of life, but
no, as in what's his Conway's?
I don't.
Yeah.
Yes, Conway's game of life.
And the order is preserved. They say in a perfectly straight line. So basically, the brute force method is like, okay, you have a bunch of rules. You look at each stone. You do the thing they do. You do it for, I think part 1 is 25 times. So, and that can easily be brute force because the numbers don't get too big. But I did tag this with memoization and big numbers, because in part 2, the numbers get bigger because now they want you to figure it out longer. But sorry, I don't want to step on your part 2 thing, but I feel like part 1 was just come up with the rules, process it. It works because you only need to know it for 25 blinks.
Yeah, pretty much exactly what you said. I looked at this. I'm like, brute force seems like an easy way to go. Let's see how inefficient it is. It solved the problem for part 1. I was like, great. I'll worry about inefficiencies in part 2, which I needed to do. Yes. I made a stone class that had a blink method in it. I don't think I cached. I don't think I did memoization or caching in the part 1.
No, I didn't do that in part 1
I
either.
didn't care to.
Nope.
But I can see but it's the same class and the same method, so I can see that I added it in part 2.
Yeah.
Part 2 went from 25 blinks to 75, and you're like, okay, that shouldn't be that much worse, except that you're like doubling the size most of the time.
Yeah.
Most of the time you're doing things because you're splitting the odd number ones, right?
Even number ones.
Or the even number
and
ones.
You're multiplying
and the odd number ones.
Numbers. Yeah.
Yeah, and the odd ones get to a huge number.
Right.
And then that is usually odd or usually even number
gets
because I
split.
think it's and then it splits and so
Yeah.
on.
So the numbers
Because we
get
were
huge.
multiplying it by what 2024, right? So it's like it got huge real fast.
Yeah.
I couldn't even get the sample to work. It took so long.
Oh, same. Yeah,
at
yeah.
75.
Yeah,
So I
that
had
too.
to start caching things. Caching did not help me right away. At least not the way I did
It
it.
didn't help me at all,
So-
so I feel like I'm doing it wrong, but go for
So
it.
I looked at the profiler, which I had put in a couple of
Days ago.
days earlier, and it immediately came in. I already just had the code written. It dumped out the files. I love that. I like my template for solving these kind of problems at this point. So looking at the profiler, I found several built-in methods taking ages, not due to how long they took to call, but how often they were called. So like some of the thing, like if I was doing a dictionary lookup, it's nigh instantaneous. But if I'm doing 10 million of them, it's going to take a little while.
I wrote the note. Maybe the bottleneck is the number of stones, not the calculations. Yep.
That is correct.
But how do you solve that? That's what I don't know.
So it turned out to be a couple of things.
Okay.
First off, I tried optimizing a few of those built-in methods out, operating on just like one term at a time, operating only on ints instead of doing string conversions. Because like I do a lot of stuff as I'm trying to debug where I will put it into a format that makes more sense to me. But but in this case, I'm like maybe it makes more sense to keep them as strings because I'm dividing them in half as a string. But like I still had to convert from string to int then. Mm-hmm. So I had to. I also switched over to using list.append instead of list.insert. List.insert is very inefficient in Python.
Really?
Well, not very, but it's order n, whereas append is constant time.
Right.
Basically.
Just
It's
add it to
boop,
the
done.
end. Yeah.
Yeah. So I switched over to that. And I'm like, okay, I think I need to combine caching with some of those improvements. So then I tried a caching idea of where my tuple that I stored as my hash was the value and the depth that you had, like the value of the stone and how many times it took to get there or something like that. It did not turn out to be useful. And that was that was to figure out how many stones I got from that point on. But a few things I realized. I took a ton of notes on this one because I really didn't like the second half. The ordering of the stones, despite it saying that they will always stay in a straight line, doesn't matter. You can look at any individual stone individually. It doesn't. You could take that, split it in half, and put it at the end. It's the same. You're going to get like the actual.
Right.
If I had to list them out, very different. But just putting it at the end, that saved a ton of time. So I never had to do a list insert, which was slow. My original caching solution was to cache the initial value and its result, like I said, which didn't really help at all. Instead, I had to use my cache to map the stone's value and its depth. Oh, that did work. The stone's value and its depth to the number of stones that it would produce after it reached its maximum depth. So if I was at step 10, right, and I'm going to go to step 75, I needed to know how many stones is this one stone going to produce in 65 steps. And that's how I stored things. Once I knew that, then I didn't have to keep calculating and splitting apart stones every time. Once I hit one I saw, boom, done.
Oh, so if a stone's value came up again, it would already know what it was going to be in 65 steps because you did it once.
Yeah. So I don't think that's the dynamic programming way of solving this.
Huh.
But it worked for my brain, which is what mattered there. And as I'm going through, of course, every split that I'm doing and every time I'm going another depth, another blink down, which is what I mean when I say depth, it's number of blinks, I'm, of course, storing those sub-results as well. So anytime I hit anything that I'd encountered before, it was just like a done deal, which made it a lot faster. The other thing I realized as doing this was that recursion is not always the bottleneck. I was actively avoiding recursion calls because I knew how big this was. I'm like, the stack's going to blow up. Even though I knew it would be easier to write the code that way. It's just because I was trying to flatten the recursion stack. Taking that out made my life a lot easier so that I could actually get a working solution. My final solution took it from this will never finish to 0.02 seconds CPU time. It was 0.2 seconds user time. So it went from this will never finish to quarter of a second, which is nuts.
I mean, it seems like the caching of that depth thing was big.
It was huge.
I didn't even think about that, yeah.
But the biggest thing was not having to do an insert. Taking out the insert made this huge. As soon as I realized that the actual ordering of the stones didn't matter, I was able to solve this.
Huh. All right.
And they explicitly say it keeps it in the same... The order is preserved. It's in bold and everything. And I'm like, oh, well, the order must matter. Doesn't matter. That was the trick to this one, in my opinion.
Huh. So now we go to day 12, which is called Garden Groups. And this one has one tag because that's as far as I got, which was word problem again. Yet another one where, just grokking what they're even asking was something that was apparently too much to ask for me on day 12. And I just noped out of this one. I did go on the subreddit at some point to kind of just, see, because once again, there's a very active subreddit for the advent of code, which is nice. There's lots of people talking about this, memeing advent of code, posting their solutions, posting questions, all kinds of thing. And I love that part of it too, just because for those of us who are not necessarily solving these puzzles every day, it's nice to have something to still feel like you're a part of the community while it's happening.
I actively avoid looking at those, and it makes me mad because I want to be a part of it, but when I can't solve them, I don't.
Well, no, I mean, so basically after day 7, I just was like, okay, I have reached the point in this year where I know personally I am not going to solve these as they come out anymore. Like I got past that point. My momentum was lost. There was a moment of grief that I had to deal with, which happens every year, where I'm like, okay, I'm not going to be part of the instantaneous zeitgeist of each day. I'm just going to be able to read about it later and wish that I could have gotten it done, but oh well. And once I got past that grief, then it was more enjoyable to just kind of like read the chatter about it. But this one, yeah, the way that some people were talking about it when they were talking about it was like, oh, well, it's really just this. It's just some simple area and perimeter math that you just have to do. And that's just part 1. I don't even know what part 2 is, but from what you said, it's not great. So how did you approach this one?
All right. So part 1, I was confused to start with about the rules regarding shared fences, but they cost separately. So once I figured that out, it was easier to do. I added 2 new methods to my grid class, connected group and groups. Connected group returns the contiguous region containing only the same cell value at the starting cell. Groups returns the list of all connected groups in the grid. So I could just be like, okay, are you in a group already? Great, I don't need to worry about you. Are you not? Okay, great. Find out what group you're in. Even if it's just by itself, then I was able to get them all. I ended up with a really hacky solution for the last part of it, where I iterated over each cell in each group and added its fence location, which I represented with coordinates halfway between it and its neighbor. So like 4.5 was my coordinate, because my grid doesn't work properly with it doesn't work properly with decimal points either.
Okay.
Quite honestly. So like 4.5, 3 is the fence to the east of 4.3 and west of 5.3 is what I wrote there.
Okay.
But that worked for part 1. Like that solved the problem. Part 2.
Yes.
Which I didn't finish, but I looked at my notes for this one. And it turns out I didn't get to this one because I just ran out of time. This is one I think I could go back to and finish. It moved on to the next day, and I made a deal with myself at the beginning of this advent that once 9:00 p.m. Pacific time rolled around, I would not look at the previous day's problem until after I'd solved that one or whatever problem of the day. And then I just haven't had time or patience to go back and do anything since then. Part 2, is the elves are trying to order so much fence that they qualify for a bulk discount. Under the bulk discount, instead of using the perimeter to calculate the price, you need to use the number of sides each region has. Each straight section of fence counts as a side, regardless of how long it is. That seems straightforward, honestly. Like, it doesn't seem that bad. I didn't even think I was going to need to modify any of my classes and only modify that final hacky part of my solution a little. But once I actually went to work on it, that didn't turn out to really be the case. The hacky thing is ultimately the problem. I know it's wrong, basically, which is I need to find the specific edge case that I'm missing, which I knew 9 days ago when I worked on this problem and don't know anymore. And unfortunately, I'm going to have to do that. I'm going to have to find the edge case by hand because of the hacky way I'm finding my fences. So I either need to which is how I was doing a lot of this. I was going to the board and I was like, okay, this one's going to go like this. And there's one here. And then, okay, that's how that works.
I feel like I need a whiteboard. Man, you keep bringing that up, and I don't have that.
I don't know how to work without a whiteboard, my friend.
Oh, man.
I had 3 in my smaller office. I only have 1 in this bigger office because I find I only need the 1.
Okay.
What I ultimately came to as a conclusion is I need to expand my class to either work better with decimal positions, like 1.5, 2, so I can print it out, or I need to expand. I need to have my grid double in size and so I can put things in between and then count that way. But there's a lot of weird conditions with that. Like the corner, there's some spots won't exist if you double it. Like if you have a box, corners of that don't, because it's a whole thing.
I mean, is it really worth keeping with the hacky thing, or is it better to go back and make it better?
I honestly don't know.
Okay.
But I know that that's where the problem is. I know I'm missing an edge case, and I can't print my grid because of the hack. So if I could print that out, that would be somewhat better. Because I'm storing it in my grid. I'm going integer values, so I would need to look for those halfway solutions or something.
Yeah.
Because if I could print it out, I could see what was wrong. But I can't print it out, and I ran out of time. That was my first day of failure. Or my first part of failure this year, and it was certainly not my last one.
Yeah, we're definitely in the thick of it at this point.
Yeah.
Each successive day after this is just I'm reading them, and I'm just I'm just doing a lot of sighing at this point. It's so annoying. It's frustrating because it is fun. But it's largely fun if you have the time and you at least have a bead on what you're supposed to do, because it can be very fun to figure out the thing by building the cool data structure and adding the classes and the methods and anyone that
and that's the fun part for me.
Yeah. Well, and the fun part for me is also when either the puzzle or the answer has some kind of visual component, like that day 6 with the guard.
Wait till we talk about day 14.
Well, it at least it's nice to have something to look at, because if nothing else, I'm ooh, I made that pretty grid or that pretty graph, even if I'm not getting an answer from it. But okay. So that was day 12, garden groups. Day 13, claw contraption. We have to figure out a claw game. Which I saw this and that sounds like fun. That sounds interesting.
I liked this one. Part 1 of it anyway.
Yeah,
I don't remember if I liked part 2.
I'm looking at my code because I did at least attempt this one. I was able to at least grok what they were asking, which is you have a claw machine. You're in an arcade now. Or no, you're in a resort that has an arcade, and maybe you can win some prizes from the claw machine. Sure, why not? If you're familiar with the classic claw game in any arcade, you normally have a joystick where you can move the claw from one corner of a grid, and you can move it a certain amount forward and back, left and right, but then you usually get one chance to press the button to make the claw go down and ultimately not grab the thing it's trying to grab, because those games are rigged. But this one's different because it costs tokens to move the claw itself. And you have 2 buttons. You have A and B, and pressing A costs 3 tokens, and pressing B costs 1 token, at least in part 1. And you have your input is a bunch of claw machine setups where each button moves the claw in a certain amount of spaces. So for example, button A in the very first setup it moves along the x-axis 94 units or cells or whatever, and then it moves on the y-axis 34. Button B does something different, as opposed to just
And that's
moving.
different for every claw machine.
Right, every claw machine, each button moves a different way, as opposed to normal claw machines where it might move like 1, 1, 1, 1. It moves a prescripted number of spaces. But then there's a prize, and that prize is at a certain location. And so you're trying to figure out what is the fewest number of tokens you can spend to make the claw in each setup get to the prize. Like what's the optimal button presses for each machine that will get you the prize?
The cheapest.
The cheapest, yeah, because each button takes a different number of tokens and they move in a different, way. So, just mapping this out into a data structure, at least for the first part, doesn't seem like the hard part. The hard part is the optimization, which is a tag that I put on here. And also I put systems of equations. I don't know if that actually has anything to do with it, but there's, I feel like there must be a system of equations.
It comes into play in part 2 for sure.
Okay. There's some system of equations where, by pressing the buttons of this claw machine in order to get to the prize, and you're trying to essentially figure out what's the best equation that will get it there with the fewest number of button presses without overstepping it. Because that's one interesting thing is there's no going back on these claw machines. There's only going from the top left corner down and right to the prize. You can't go back left or go back up. So you either get right to the prize or you overstep it and you don't get the prize. So that was an interesting wrinkle. But I didn't get far enough in this beyond just trying to map out whether, the machine and how it works. So yeah. How did you approach this one, Matt?
A couple of different ways, actually. For part 1, I upfront calculated where you'd end up by pressing each button X times from 0 to 100. So I just had it because part 1 had a limit of 100 button presses.
That's right.
Which I really appreciated. Because it gave it a very easy bounds to solve the problem. Yeah. I'm like, great. So I just stored literally, okay, you press B once. You end up here. You press B twice. Go here, right? You press, and then I knew that based on A and B, and then I could just add them together and just math. And then when I actually went to solve it, I looped through B's offsets first, and then checked for what was needed in A's because B cost less than A. So I assumed move B as far as you can and then do A. For part 1, that worked. I thought I was going to end up with the wrong answer, but that worked. I ended up with a fun little one-liner solution to the last bit, which I calculate all the solutions that you can get and store them within 100 button presses. And then I calculated the minimum, and then I mapped a lambda that just was 3 times A plus 3 times number of A presses plus B presses over solutions, and then that just gave me the answer, which was great. So once I calculated the solutions, finding the cheapest one was super simple.
See, yeah, that was. I wasn't sure how to even approach finding the optimal path. I was thinking there had to be some equation where you press, B, 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 A, B, B, A. I didn't even think to do something as simple as press B and then try A until you get it, and then press B one more time and then see how many times it takes A to get there. I don't know.
Yeah.
That's great. I'm glad it was that easy.
Plus pre-calculating. Yeah. That plus pre-calculating all of the things made that really simple, because then I only ever did the calculation, which isn't hard, right? I only ever did that calculation once for each number between 0 and 100 for each button, and then just added them together. And my position class does all the math for me. I figured that out 2-3 years ago, and I have not had to touch it since. So if I add a position and a delta, I get a new position, and I don't have to think about it. I even use the plus operator, so my code looks easy. It's easy to think about. Love that.
Okay, so now I'm guessing that part 2 threw a wrench in this somehow.
Part 2, you add 10 trillion to the X and Y positions of every prize. 10 trillion with a T.
Big numbers. All right, adding big numbers to the tag.
And 100 is no longer the cap. There isn't a cap, which meant I had to throw out everything. Basically, my part 1 just wasn't going to work there.
Okay.
I tried it. It was too slow. So I decided I needed to go more mathy. And you hit the nail on the head with the solution I went with. But some potential solutions that I went down the route of was least common multiple. I'm like, maybe there's something there. So I investigated that for a while. And there still might have been, but I didn't come up with it because that's part of math that I don't understand how to use. There's a whole Chinese remainder theorem that pops up every year.
Yeah.
That I can't quite grok.
Yeah, I've heard that one.
I think I tried that, or that might have been for a different problem, but I think it was this one. My search was very linear. I was starting at one end of B and going to the other. I'm like, what if I tried to do a binary search? I never even tried to do that because it was just way too complicated with the code. Mm-hmm. Or do a system of equations thing. I did the system of equations thing. I did this all on my whiteboard. I wrote out like how you would solve for B, basically. I put A in terms of B or something like that, and then just I equated them, and then I was able to get it, and it worked. And then I actually ended up wiping out my original solution, so I don't actually have what that looks like anymore in my code. I'd have to go back and look at the history. I'm only using that thing now, so I put that system of equations in here.
So I was thinking ahead. I just because that's all I was doing, all that kind of stuff for part one. I was like using like online equation solvers, like trying to figure out there's got to be some connection between this, and I just didn't realize I could solve part one without that.
Yeah. So solve. Oh, I didn't end up using that for part one. I lied. So solve. Let's see. I have AX and AY is converting A to... okay, that's just cleanup for myself. So A, the number of button presses that were required for A, was the Y position of the prize times the X position, or the X offset that pressing B gives you, minus the X coordinate of the prize times the Y coordinate, or the Y offset that B gives you, divided by, and floored, the Y of A times B of X, or X of B, minus A of X times B of Y. That was A, right? And then B is like positions X minus X's offset times A divided by B, floored.
I'm amazed that you came up with that. I knew I had to do something like that, but wow.
It took me forever. Like I haven't done system of equations in years. I actually left it on my board until my daughter got home. I was like, "Hey, you remember doing this last year in math?"
Oh my god!
This is the last time I did it was when I was helping her with her homework. And prior to that was years ago.
Yeah, I remember. I think I don't know. I think it was last year. There was some kind of snowball throwing puzzle near the end that required systems of equations. That was the last time I remember thinking about that.
I find it really interesting. Richard, who will be on our final episodes of Advent of Code this year, posted a flashback of a previous year in our channel earlier, and it's one where he solved the problem by literally, like, he had to put out a piece of paper and like cut it up so he could figure out how to fold something in three-dimensional space. I find it really interesting when these problems end up being a solution that isn't code per se and requires you to like do something like solve a system of linear equations and then put that in your code, or print something. There was at least one I've done in the past where I actually did solve it by hand because it was just easier for me to do that than try to write code that did it. It was like people shuffling rooms or something.
Yeah, I remember that one. Yeah. I mean,
I solved it by hand.
I mean that's the thing about this challenge is that these are logic puzzles. You know, they're not necessarily programming puzzles. It's just that programming is a very useful tool to figure them out, especially once the numbers get huge, you know, because computers are just way more efficient at computing things.
And my problem is I like to solve problems with code. I find it fun.
Yeah.
And so when it gets beyond that and I'm like, then I lose interest. I want to come up with a clever, object-oriented way of doing it every time. That's right. What it boils down to.
All right. The last day for this episode, day 14, restroom redoubt. I see positions, I see vectors, I see robots. I see a lot of like after a certain amount of seconds, things have changed. I honestly didn't even get to this one, but it looks like it would take me a while. That's all I can say. That's all I can say.
Part 1 was pretty easy.
Okay.
You could definitely do it.
Okay.
Basically, I just stepped the guard 100 times, each guard 100 times. Like I brute forced it.
Okay.
Or I was going to brute force it. I actually ended up doing math for it, but I think brute force would have worked, which was like, I'm actually trying to find it in the code because my pseudocode doesn't make sense to me.
That's not good.
It was so it's your position, right? So I made a guard class that extended from position. And then it's your current position plus your velocity times the number of times you're going to move. Mm-hmm. And then I just modded the X by width and modded the Y by height. Because I think he wraps around. So I was going to step through it. And I was like, well, I don't need to do that because he just walks in a straight line. So I was like, great, go do that. And then I'll just make it so that you're back in the grid. So my move steps logic was very, very simple. It's 4 lines of code. My actual solution is more complicated than that because then it has you calculate quadrants, like to score the safety factor or whatever. It's like score this quadrant and this quadrant. So I had to like split it up to figure out where the quadrants were, and if it's exactly on the line, don't count it. And like there was a bunch of that was more complicated than my actual figure out where the guard's going to end up.
I remember reading that and being like, "Oh, that's an interesting grid that they're showing there." Okay.
Part 2 is the only one I so far have an asterisk for this year. I did, in fact, go online and find information about it on Reddit because I could not solve this thing to save my life.
So what's the twist, though?
I'm going to read it. It's only a paragraph.
Okay.
During the bathroom break, someone notices that these robots seem awfully similar to ones built and used at the North Pole. If they're the same type of robots, they should have a hard-coded Easter egg. Very rarely, most of the robots should arrange themselves into a picture of a Christmas tree.
The Christmas tree.
What is the fewest number of seconds that must elapse for the robots to display the Easter egg? I hated this problem.
Okay, this one seems so vague. That's what I kept saying.
I'm still
online.
angry about it.
It's very vague.
I'm still mad about it.
Okay.
20 days later.
Because it's like, it will look like a tree. But yeah, what does that mean exactly?
Also, part of what threw me off on this, most of the robots, so it's not even all of the robots. So I'm like, and they don't give you a picture of the tree.
Right.
I'm like, is it a straight-sided Christmas tree? Is it one of those like zigzaggy ones? Does it have a trunk? Is it the whole page? Is it small? Tell me something. So I literally just had it iterate and print it out, and I held down the enter key and watched it. And I never saw a Christmas tree.
Okay.
So then I tried changing how it was printing out so that it was like left shifted, basically. So I was like hoping I would see a triangle more easily.
Yeah.
Didn't work that way. I eventually went online. I'm like, what the hell does this stupid Christmas tree look like? So I can find it.
Yeah.
So I at least know what I'm looking for. And the hint I found was not actually what the Christmas tree looks like, but it was a trick that they used to find it, which was when all of the guards are in different positions from each other, so no one overlaps.
Oh.
That is when the picture will form. You won't see it before then. So I only printed things out if there was only one guard in a position, because they could overlap in the previous ones.
Yeah.
I saw people literally create movies to show it. I saw people do what I did. People tried searching for, they tried to use the safety factor from the previous thing. Like, everyone struggled with this one.
Okay.
If you know what the Christmas tree looks like, it's actually incredibly simple. So I won't tell you that part, because that feels like cheating. But calculating where they're all going to be and having them at different positions is fine. I actually printed out the final result I copied the final result and put it in my notes. The biggest important thing was most of the guards form the picture, not all the guards. Because I think I might have found this when I was doing my enters, but there were all these weird extra guards wandering around, so nothing was in a Christmas tree shape. Mm-hmm. So I was like, well, that can't be it. And that was after I had done everything where I had changed it so it was all collapsed to the left side. I was just like, I was getting rid of white space, like, unless it was between. I don't remember what I did. I tried a bunch of different things just to be able to like, try to visually see it, and I never did. Like I probably blinked the first time at 6,512 frames in when it showed up for me.
This one seems very odd for Advent of Code that what they're asking you is that vague. They're usually not anywhere near that vague.
I was like livid about it. This is what actually stopped. Like if you look at when I solve problem, you'll see I just basically stopped after day 14. I've done like one since then. And it was because of part 2 of this. I was mad. I'm like, this is not fun. This is a dumb problem. It's not solvable by a computer.
Yeah.
Because you don't have the relevant input to solve it.
But
like,
you
don't
back,
have enough information.
You came back for 17 though, because we both got that one. So
I've read them every day.
Yeah.
And 17 sounded fun.
Yeah.
Today's also sounds fun. The 21st.
Yeah.
So I'm probably going to try that if I have time in the next 3 hours.
Yeah. I mean, yeah, at this point, it definitely is very much about time and whether you're willing to put the effort in. But wow.
I'm not.
I just remember, I remember looking at the subreddit that day, and I didn't know what day it was, but yeah, it was day 14, and there's so much like, what is it even supposed to look like? This, yeah. So that was a pivotal
It
moment.
looks like if you do the movie version, like where if you actually like display all of them, it looks like static for quite a while.
Yeah.
And then like all of a sudden like snaps into a picture and then it's static again. It was like, sure, if I could have seen that, but I would have had to display them. I would have had to set up my code so that it automatically advanced every like half a second or something where I could actually watch it instead of holding down the enter key.
Yeah.
Because what I was doing is I would do that and then it would like see something that I'm like, maybe that's Christmas tree, and I'd scroll back to like see what it was.
Yeah.
But I think what I saw people doing was actually saving them as images and then converting that into a GIF or something. And I'm like, nah, I'm not doing that.
I mean, you know, after 10 years of this, like Eric has got to be, you know, he's got to be racking his brain to come up with new, interesting, wild stuff. Because even the stuff that he does come up with, I mean, you know, you can see the lineage to previous puzzles that he's even calling out in the puzzles,
especially this year.
Yeah, but even then, like you know, you got to keep it fresh. And how do you keep it fresh after 10 years? You know, you got to try wild stuff, and sometimes it lands, and sometimes it doesn't. I don't know.
Yep. I think if it had said how long until it gets to a
picture.
Anything with more information.
Yeah.
Right. Because that was the problem is you actually did have to print them out and look at them.
Yeah.
Or make an educated guess about something like whoever figured out the guard being in different positions thing.
Yeah.
I figured they were all going to collapse into like a small picture or something. So it's kind of like 1, 2, you know, something.
Yeah. Oh. All right. Well, I will probably at least try the first part. Yeah. I don't know. After that, after talking about part 2, I don't know if I'm even going to get to that.
There are a bunch of hints I can give you for part 2 to help you find it.
Yeah.
Like there's like several different ways of finding it programmatically.
Yeah.
Just none of that information is in the problem statement.
Yeah. All right. Well, that's day 14 of Advent of Code 2024. I think that does it for this episode. That's enough brain breaking puzzle logicking. I hope you enjoyed this episode. We will go over more problems in a future episode. But if you want to listen to our previous episodes, of which we have many, about the first 7 days and the previous 3 years, 21 through 2023, you can go to hackingthegrepson.com and listen to those. Until the next time we come back at you with more Advent of Code puzzles, we now return you to your regularly scheduled lives, already in... I totally blanked out on what I was supposed to say.
Progress.